That's a fourth of a cycle. It's a fourth of a complete cycle is to start here, swing over to there, swing back to where you began. That's your complete cycle. But a fourth of a cycle is from here down to equilibrium, okay, at the ground state of this, which we call ground state 2 from quantum. And then come back up. Now you're at the second fourth, then the third fourth, then the fourth fourth. So we go through 4 phases, and we'll show the 4 phases tomorrow in class, on Tuesday in class. When we're talking about spring. Same idea though, springs and pendulums, I teach them at the same time. So x max, negative x max, 0, it's going to be cosine, right? It's a cosine function because you start off with an amplitude. Alright, it's cosine world. Yes it is. Keep going here. Moving right along, page 3, I got 23 minutes to go. Page 4 is pretty quick though. You know what, I'm not going to go through and derive this thing. This was done in 5.7 in detail. And I will post that key. So I'm going to say refer to key. So you can do it. You could do it in you could do it in 4 steps, or you could do it in 5 steps. Go to purple. So refer to key 5.7. I will get that up. MUIRS. All right. I will get that up. That's so funny. I don't have much time. I always get mad at you guys for waiting to the last minute. Don't wait till Wednesday night to do the reading. You know, thinking about myself. Wait a minute. I'm waiting till April 15th to finish my taxes. So, hey, you know, it happens to all of us. It's all about priorities, right? Where's that secret word at? All right, now we get to this one, 12. This is a multiple choice question about the concept we learned when we did the demo in the hallway. Remember that with the ruler, and we had the ramen noodles, and whoosh, one went out twice as fast as the other one because of the whole radius thing and omega. Whoosh, it went out. Now, remember the one that went out twice as fast? How long did it take to stop? Enough said. That's all I'm going to say. Check your notes. It helps to be in class. All right, I'll find that from somebody. But that's all I got time to say on that. Or remember the formula for kinetic energy is 1/2 mv squared. All right, where kinetic energy says the work done by friction is going to equal the change in kinetic energy. Well, if it stops, the final velocity is 0. And we actually showed the equation. That won't be necessary. This isn't even a problem. It's just multiple choice. You can do it in 10 seconds if you read it carefully. Okay? Now let's get to one that is a problem. I want to spend some time. I've got 20 minutes. This and the next one will take most of my time. All right. This is one. I want to see how you're going to do it. It's going to be a challenge, but luckily you're watching. So this one is, it says use the work kinetic energy theorem. You have to use it to solve. And we have a 2,000 kilogram car, so it's this is more of a drawing, not really not a free body necessarily. I mean, I'll show the forces, but it's really, when it says a drawing, it means there's going to be distances involved or time, things like that. So we do have mg down. We're going to have normal up. It's not going to play any role. At least as far as the work goes, because it's 90 degrees. So, and then I have the force of friction back, and I don't care. It doesn't say if it's kinetic or static. It's static, I guess, if it's rolling. But anyway, 4 meters long, so I have I'll go a different color, I guess. This is 4 meters long. That is sloped at 13 degrees. And the one on the test is very similar to this, changes the numbers around. With the horizontal, if the average frictional force is 1.8 kilonewtons, so we're going to have, that's 1,800 newtons. Might as well get it in the right form. Impedes the motion. What is the speed of the car at the end of the driveway? So, very simply put, This is the work done. It's the summation of work. Remember the pocket version? Summation of work equals change in kinetic energy. That's the pocket version of the most important theorem in mechanical engineering by some accounts. So let's add up the work done. Well, I have the work done by gravity, and gravity's going to help. See, remember I said if it speeds the object up, it's helping. That's positive work, or you can look at it also by the angle. And that'll also tell you that. And friction is going to be negative. Of course, it's always cosine 180. So plus the work done by friction, and I could say the work done with the normal force, but that's going to be 0 because cosine 90 equals my change in kinetic energy. Well, that's 1/2 mv final squared. It says it starts somewhere here. It says from rest. So initial kinetic energy is 0, 1/2 mv naught squared. So I'll leave that part off. Well, the work done by, I'm not going to end up, I'll just get the symbols and then give you the answer. Let you do the number crunching. The work done by mg then is going to be 2,000 kilograms times 9.81 meters per second squared. There's my mg. Times cosine, well, let's go and do times the 4, then cosine of the angle between the displacement and mg, which in this case is going to be cosine of 90 minus 13, or 77 degrees. All right. Plus the work done by friction, which is going to be 1,800 newtons, times 4 meters, times cosine always 180 for friction, because it always the opposite direction of motion, equals 1/2 mass, which is 2,000 again, times, so we're trying to find, v final squared. Now, I kind of jumped the gun. I could have gone ahead and solved for v in symbol form, and then I think it's what I did on my worksheet here. Yeah, but you don't, I'm not going to ask you, I don't think, to do it. But I just wanted to show you, there's the numbers, you punch them in, and you're going to get, if I punch my numbers in right, you're going to get v final equal to 3.23 meters per second. Okay? But if I didn't punch them in right, there's your Murphy's Law. I'm always going to screw up somehow in number punching. That's why I like the symbols. Okay, good, did it. Now, down to 17 minutes, and let's check our secret word. Secret word, there's not much room where you're going to put it, so it's got to be short. And since it's getting close to the end of the year, might as well go for it. It's May, the lovely month of May. Merrily appear, it's here, the lusty month of year. That's from Camelot. Winterbeer sings it. So it's May, M-A-Y, May. There's your secret word, May. It's a coming, folks. On to the great beyond. Farewell to my seniors. Juniors, I'll see you next year. Alright. See everybody on Facebook, I suppose. I'll always see my seniors again at the physics picnic. Alright, well, let's not get sad. I'll start getting verklempt here. Okay, now let's do 14. This is the last long problem. And then we'll just briefly talk about the rest. 14, Joe Dynamo here is going to jump off the Vista building. And this is really an easy problem if you know anything about conservation of energy. Remember, we said, and I didn't make this too hard because I knew we hadn't spent a whole lot of time on it. So we said that EI, this is all from 5.7, equals EF. And so if I put that in, that's all I know so far is MGHI plus 1/2 MV naught squared equals MGHF plus 1/2 MV final squared. And the reason why I haven't spent a whole lot of time on this conservation of energy is I'm getting the Hooke's law, I'm getting the spring energy. We're going to get that next week. We're going to stick that in, and then we got a really nice conservation of energy. We're one step away from getting ultimate fighting tool. So I'm kind of waiting to hit a lot of problems, but I'll do this one here. What's Joe's gravitational potential at the top? Well, it can't be any easier. Don't miss this problem. It's not hard. It's simply mghi. Well, he is 800 newtons. That is his mg. So we have 800 newtons times his h, which is 24. That's it. Multiply those, and looks like you got 19,200 joules. Remember joule. Joule is a unit for energy. Newton meter is a unit for work. There's a difference, though, which we'll get to later. There's a difference between work and energy. Work is where you're changing. Where work kinetic energy, you're changing energy by doing work. Part B, what is Joe's kinetic energy halfway down? Well, notice that ultimately he has no kinetic at the top. He's standing still, so his velocity is 0. So that's total energy. That is essentially EI, since all of it is potential to begin with. So as he falls, his H changes and his potential drops linearly. Well, that means the kinetic energy grows linearly. So halfway down, all you got to do is cut this number in half. But it's asked for speed. That's the thing. It says it says kinetic energy. Okay. So kinetic energy halfway down is simply this cut in half, and 9,600, which is 9,600 joules, just 1/2 the total energy. All right. So it's equally shared halfway down. Now his velocity is not linear. Velocity changes as a square, but that starts off being 0. So his velocity changes as a square. Anyway, the next question asks, find Joe's speed just before he hits the ground. Now speed means the absolute value of velocity, so it can be a positive number here. And you must solve this. I want you to solve this by conservation of energy. You could go to blue mirror, but I'm going to take off. If I don't see you using conservation of energy, you're going to lose some points. But you'll find that the great equations reduce down to the simpler, I'm pointing to blue mirror, the simpler kinematic equations. That's what makes them a great equation. They encompass equations that are beneath them on the abstraction scale. All right, so find Joe's speed just before he hits the ground. Well, that's 1/2 mv final squared. But at the end, all the potential's gone. There's really no more height. I mean, maybe there's a millimeter or a micrometer, but that's essentially nothing. You have to realize that. Yeah, he's still moving. He hasn't hit the ground yet, but it's almost all kinetic, close enough for me to say it's 19,200 joules. And I would always have a student that'll say, no, it's 19,199. Okay, fine. That's what you want to do. But just say he's closer and say it's so close that it rounds to that. 19,200 joules. So now all I got to do is I know the mass. The mass is, that's 800 divided by 9.81. Okay, so I got to do a little bit of manipulation there. And I end up with, when you're punching your numbers, you got 800 divided by 9.81 there. Punch it all in and you find that his final velocity, using these numbers, if once again I am correct, and Murphy's law does not rule, 21.7 meters per second is the velocity just before he hit the ground. And the last question states, what's Joe's approximate potential energy, which is UG, just before he hits the ground, and that is 0. Pretty much all of it. Remember this thing about money in the bank? He's used it all up, and now he's at the bottom. Okay? So there is that one, and I'm down to 10 minutes. Okay, let's go to see what else we got. Oh, okay, these are questions about Hooke's law and the anagram. We've been talking about this. I'm making this video here. I'm not in the middle of the video, but I got about 10 minutes to go. What's going on with you? Okay, well, you just come back to, where are you at? You're still in my room. Well, you want to just start heading over to my room and bang on my window, or what do you want to do? I'll call you when I'm done. Okay, bye. All right, so that's Hooke's law. Now we found Fa equals Kx, but Hooke was had objectophilia. Was my theory anyway, and that is that he loved instruments so much because he really didn't get along with people as that well. I mean, he had friends, but he spent a lot of time in the Royal Society. He was the kind of the guy that did the experiments, and so he came at it from the springs point of view, which makes sense to me. So the springs point of view is negative kx, and that is, when we said that is the spring constant, it's newtons per meter or it's pounds per feet, but it's some kind of force over position. The anagram, when we did that, we said CE, I, went on and on. It's on 5.9. And I'm going to give you that anagram. You got to unscramble it. I'll let you do that. And let's set a question about the anagram. So, tensio sequis, boom! That's Hooke's law. As a stretch, so the force. Okay, let's go to the last page. The last page, if you're here on Tuesday, then you should be in good shape on this one. We're going to spend Tuesday and a chunk of a little bit of Wednesday. We'd love to be able to move on Wednesday onto something else, some packet 6 stuff. But if not, we'll go ahead and do this. We started this actually today. Remember, we did this one today, and you can take your choice. But if my direction of motion, this is the first. Remember I said that, like on a pendulum, it's really broken up into quarters. And this, if this is my starting point, if this is my starting point here, and I'm going this way, if that's where I start, then this represents the first quarter of my trip. And one trip is an oscillation. This represents the second quarter of my trip. All right. And if I'm if I'm back over here and working my way back this way, this is my third quarter of my trip. So first quarter, second quarter, third quarter would be on the way back, and fourth quarter, I'm still going this way, back to where I started. And there's some weird things that happen here, which I think we'll get into a little bit starting tomorrow and definitely on Wednesday. But we plotted Hooke's law, and we said, okay, since it's negative, since it's the force of the spring equals negative kx, this is being my x, right? And x is 0 here. We're at equilibrium. Here's negative x max, where maybe I'm starting. If I'm starting off compressed, if I got that spring compressed, then I'm starting at negative x max, and then it's working its way. Now it's at equilibrium, but because of inertia, it's going to keep the box's inertia. It's going to keep pulling that spring. The spring doesn't want to do it. The spring's going to get mad. So it pulls that past equilibrium, reaches a max out here, and then starts to head back. And you say, Mr. Askey, you're obsessed with springs. You got your little spring collection. You're like sick. Well, and I wasn't. I was not obsessed with springs until I started realizing how much of not just physics, but quantum, what happens in the nucleus, what happens in biology, all these things, what happens in airflow, all these things are elastic, have elastic properties, what happens in sound waves. It's all about elastic properties, which starts with the spring, and it's with Hooke's law. So Hooke was on to something. So you'll keep coming back to this. If you go any kind of science or biology, okay, for all you pre-med types, you'll come back to this kind of spring thing, especially chemical, microbiology. If you're dealing with chemistry, you'll deal with a lot of things because atoms are connected up, like with springs. Okay, and they're always using these. Someone made me a nice benzene ring here, but they always this is how they'll. Man, it's $100. This is how these things, they're always vibrating. That's vibration of solids is what gives them their temperature. That's the only kind of movement that a solid can have is vibrational. So in solids, especially, springs dominate. I mean, vibration is the number one mode of movement. Okay, stall long enough. So comes across my first quarter. I'm in this triangle, and someone said, "Hey, it's the bow tie." In class today, and I was, yay, you're right. So it's a little early, we couldn't talk about it yet, but see, for this first quarter, I'm in that triangle, and when you find the area under there, and I don't know how much of that we'll get into, if it gets into it on the journey, the journey I'm talking about is the last sheet. Anyway, here we are. That's the basic thing is, remember that the slope of this is negative K, right? So something that's really, that would be like a weak spring. A really strong spring might have a slope that looks like that. And these are what's called Hooke's Law springs. Now, you could get a spring that doesn't do it, that isn't linear about how it might, there's certain reasons why you'd want that. A spring that maybe the more you compress, it's exponential as it resists. And that's going to be, you know, maybe look like, maybe come down and look like that and then come down like that. But it can happen. We deal in this class, it's hard enough dealing with the force changing over time and changing over position. That's difficult mathematically. So anyway, we're only going to worry about this linear stuff. And so if that's the case, then we're going to have a triangle here. And the area of that triangle is going to represent the work done by that spring. And then, as you notice, we've done this before, but when we go down here to this one, now I find the area here, well, that's also work, but now it's negative work, right? So that's negative work, so the spring's doing negative work. And when you bring in work, which is a force times the distance, now all of a sudden you start to talk about energy. So now we talk about not just the elastic force, but the elastic energy, and then next week we take that and put that with our other components and work our way towards the ultimate fighting tool. And then we get down to so that's what these kind of problems are like. So I guess enough said there. Then we get down to 17, and 17 is not a hard problem at all. (17) is, all you got to do here is probably just, it looks like it's just using Hooke's law. So we have Fs equals negative Kx, and it's a matter of plugging and chugging. What's the maximum number of inches? Tricky. You can stretch a spring from equilibrium with spring constant of, and then, okay, they're going to give some crazy units, it looks like. 500 pounds per foot using a direct, it says applied. So I'm not going to use this, I'm going to say Fa, because it's applied force. That's spring force. Fa equals Kx. That's what we actually graphed. Our first time we put the weights, we were doing an applied force. So it looks like I'm going to use this equation. So applied force of 40 pounds. So I'm going to have, I agree, X is going to equal Fa over K, but now you get all these crazy units, inches, feet, that kind of thing. So you got to watch out. I didn't work this one, it looks like, so I'll at least plug in the numbers. Fa, let's do that. Okay, let's do it in pounds. So I have 40 pounds over my K is 500 pounds. That's going to cancel. And that's going to be over, and it says how many inches. And so let's do it in 12. That's a foot, so 12 inches. And it looks like when I do that, the inches come back up top, and I have my answer. Okay? Whatever that happens to be. All right. So that's the test. Remember the bonus. You're going to have 4 bonus questions. Go to the physics, just physics history, 1946 to 1952 or something like that. It's on the website, and click on it. And it has 8 things, and I'll take 4 of those 8. I'll ask multiple choice, try and make them obvious that if you looked at it a couple times, you'll get those right. All right, well, good luck. And this may be my last review video. I think packet 6 I'll probably do help videos again. I don't know. All right, so good luck to you.